So the inhomogeneities in the microwave background were a very powerful tool for us. The reason is that the wavelengths of these primordial sound waves gave us a standard ruler. They gave us an object whose length we actually knew from physical considerations. We knew the distance because we understand the microwave background and its cooling and its coupling to hydrogen. So putting those two together, we managed to run a small angle approximation on a triangle whose long side was 46 billion light years, or 40-some billion light years. Brilliant. How nice would it be if we could have such standard rulers at other distances? Well, it turns out that we do. Understanding them will force us to study the sound wave in slightly more detail. This takes us, as I said, outside the realm of strictly homogeneous cosmology. We'll have to deal with inhomogeneities. Calculations become a little complicated. We will say some things about what the results are, but this is an essential topic, and I think we can get something useful out of it. So I'm going to claim that these primordial fluctuations in density actually leave a signature that we can pick up at nearer distances. What do you mean at nearer distances? Aren't those fluctuations? Well, remember, those fluctuations occurred everywhere. When we observe them with the cosmic microwave background, we observe the photons emitted at last scattering. But can we observe echoes of that same structure nearer to us and therefore in the more recent past? The answer is yes. See, the idea is that these sound waves in the early plasma are, in fact, the seeds that produced the inhomogeneities we observe in today's universe, galaxies, clusters, and perhaps most importantly, the large-scale structure of those voids that we saw in the deep sky surveys. And we can make measurements of the density of matter or baryons in the universe in several ways. We can track galaxies and clusters and compute their correlations. We have those core samples of light from pulsars that give us a distribution of hydrogen density along a line of sight through the Lyman alpha forest of absorption lines. And we can use these to try to understand, relate these to the expected structure of the distribution of matter. Now, how does a sound wave in the primordial plasma result in a distribution of galaxies? As I said, the calculation is complicated. This iconic figure over here on the right perhaps demonstrates what it is we're talking about. This is sort of a sequence of the results of a simulation in which we start at a very early time, probably near the end of the radiation era, with a perturbation. At some point in the universe, there's an extra density. Now, this density, because everything is strongly coupled, occurs correspondingly in the blue, representing the baryons, or gas as it's indicated here, the black indicating dark matter, and the red indicating the photon gas. And so we have a region that is compressed and hot, and therefore has both a higher density of gas and of photons, and also a higher density of dark matter. The green line is the neutrinos. We will leave those. Those are parts of the details we don't have to worry about. Now, we know what happens in the early universe. The baryon and photon plasma are tightly bound together, and in that hot plasma, this perturbation will travel as a sound wave, so that if you produce a region of high density, it will spread radially as a wave. You will get something that looks like a ripple on a pond, except in 3 dimensions. And this wave, in which both radiation density and dust density increase, moves out at the speed of sound, which is 1 over square root of 3, the speed of light. And what we see here is indeed that the dark matter, which is not strongly bound to the plasma, remains where the original fluctuation was. The matter and radiation move outward, and you basically obtain a ring or a thin spherical shell expanding around the initial perturbation where you have increased density. Of course, this shell does interact gravitationally with the dark matter, so some of the dark matter is being dragged gravitationally along with the baryonic matter. And then, around the time of decoupling, of course, what happens is that the photons start to leak away. The photons decouple from the baryons. The baryons are now left without a restoring pressure. There's no extra radiation pressure. The photons have streamed away. We now have the cosmic microwave background. We now have a wave of higher density baryons, but it's only interacting gravitationally. There is no increased radiation pressure to cause it to continue to move. So from a traveling wave, we have this frozen ripple of increased baryon density. In the center is the increased dark matter density, and over the next few millions of years, the gravitational attraction between these two concentrations drags some of the dark matter out to where the baryons are, and some of the baryons back to where the dark matter is, so that the result is that if we started with a spike at some place in the universe of extra density, at the end of the day, what we have is a ring with a spike in the middle and then surrounding it a spherical shell, both of which exhibit enhanced density, and the distance between these is d horizon over square root of 3, as we mentioned before. This is the distance that the sound wave in the plasma moved during the time until decoupling. And this is the picture that is frozen. Now, this is what happens if we had one perturbation. And if there was one perturbation, then when we looked in the sky, we would see one cold spot. Remember that higher density corresponds to a cold spot, surrounded by a cold ring. Now, of course, we don't see that in the microwave background. We see this random distribution. The point is that there were many such fluctuations occurring everywhere. All we noted is that if you find a cold spot at one place, you are more than likely to find another cold spot at a distance corresponding to d horizon over the square root of 3 elsewhere in the sky. And so this increased correlation is a result of imagining that random pattern that we saw is a superposition of many rings of equal radius scattered randomly across the sky wherever these original perturbations were. Where did these original perturbations come from? We'll leave that for later. So, as we said, this predicts, now these regions are now frozen. We have increased baryon density and increased dark matter density in these regions. So this is the region in which, into the future, galaxies and clusters of galaxies will form preferentially, because the dark matter pools and the visible matter will fall in to these gravitational wells. Remember, there's more dark matter, so but the dark matter can't clump tightly because it can't radiate away energy. And so the baryonic matter will radiate away its energy, collapse and clump, and those clumps will fall into the gravitational wells already occupied by the dark matter. So we expect to find galaxies everywhere in the universe, roughly in those troughs that were created by these rings. So scattered around this ring, you will, if you find a galaxy that formed in the center trough, you expect to find galaxies somewhere along the ring. So again, the distribution of galaxies will be the superposition of a bunch of spheres. Now note, these are spheres at large distance. Well, in today's units, about 150 megaparsec. In particular, these are way outside the domain of gravitational binding, so these points are unbound. These distances grow. In particular, d0 is 150 megaparsec, but this is the size of these regions today. But at any previous time, we can get the size or the radius of these rings by scaling by the scale factor. These are actually co-moving. The galaxies in different parts of these rings independently participate in the Hubble flow. The point is that because these are the regions where galaxies form, well, we can see galaxies all the way down to the present. So we can measure, unlike the CMB where we only measure at 380,000 years, we can measure galaxy distributions throughout the universe, or Lyman alpha forest distributions of hydrogen throughout the universe. And so this gives us basically a standard ruler at any value of z. And in particular, the angular size that we expect for the two-point correlation function between galaxies at a given z is given by taking this distance, dividing by the angular distance to redshift z, and if we remember that d of z is d0 over 1 plus z, the angular distance is the coordinate distance divided by 1 plus z, we get this calculation. This is amazing. This means that if you measure the angular size at which you find a peak in the correlation function of galaxies at some fixed redshift, so look at a sphere at some fixed redshift, you measure that angular size, you know this value of 150 megaparsec, you are actually discovering the coordinate distance directly to that redshift. So you are making a direct measurement of the distance redshift relations, and in particular, the first such large-scale survey of galaxies was done at redshift of 0.35. And by measuring the angular distance at which they found correlations, the first peak, and the angular distance at which we find the first peak in the cosmic microwave background, you are directly measuring the ratio of the scale factor between a z of 0.35 and a z of 1,100. And of course, you can do that at larger values of z as long as you are able to do deep sky surveys. And so this gives us, in a sense, a way to map the function d of z, which is tantamount to measuring a of z. This is a very powerful tool. So we can measure d of z. This is tantamount to measuring a of z. Interestingly, when we do Lyman alpha forest calculations, we don't have angular variations because where we have Lyman alpha forests depends on where randomly quasars are distributed. What we do have is a correlation in z. But remember that we expect these ripples in the primordial plasma to be roughly spherical. So we expect the same range, the same correlation distance in angular distance transverse to our line of sight to any direction in the universe, which is of course all the same. And we expect a similar direction, a similar correlation in the radial direction away from us. In other words, if we find a galaxy at a given redshift, which corresponds to a given distance, we should have a higher probability of finding a galaxy at a given delta z, a given radial shift closer or farther than that galaxy. And we can relate the delta z at which we expect a correlation to this value d0, which in coordinate distance is about 150 megaparsec, which is the size of the ripples, the 1 over root 3 of the horizon distance as in today's coordinates having expanded. How do we do that? Well, suppose that we have somewhere in space a spherical region. Remember that its size is d0 in coordinate distances, and we're looking at it from here. Then, of course, we can make the small angle calculation that we did before. But we can also make a calculation along the radial direction because we expect a spherical distribution. So imagine that the center is measured at a distance z star, at a redshift z star. Then light from the far 150 megaparsecs farther than that will, of course, have taken a little longer to get to us. Because it took a little longer, we're looking a little farther, we expect a higher redshift. So the far end of this spherical shell will be detected at a slightly higher redshift, and we want to know what we expect delta z to be. How do we know what delta z will be? Well, we know that the time of travel of light from here to us, or from here to us, well, this differs by the little bit of extra distance the light had to go, which is this 150 megaparsecs. But it's not 150 megaparsecs, it's 150 megaparsec today. Remember that if you want, it's 150 megaparsecs today. It was a smaller distance back then. Or if you want to think a bit otherwise, remember that the coordinate speed of light is not a constant, it's c over a. So in the past, light appeared to have traveled faster. Either way you want to think about it, the time difference between the time of propagation of light from here to us and from there is given by the distance, which we can evaluate at the scale factor at z star, divided by the speed of light. And so cleaning up my demonstrations, the time difference between the two signals is d at the time z star, which is d0 divided by 1 plus z star, divided by the speed of light. Now, over this time, the scale factor increased. Since we're seeing the far end deeper into the past, the scale factor was less when we observed it than when we observed the center. And how do we figure out the change in the scale factor? We take the rate of change of the scale factor and multiply by the elapsed time. The rate of change of the scale factor, remember that the Hubble constant at any time is the rate of change at that time of the scale factor divided by the scale factor. So we write that as the rate of change is the Hubble constant at time t star times the scale factor at time t star. And now my job is to evaluate z at time t, or t plus t star plus minus delta t. So what I want to compute is the scale factor z at which we observe the distant end, the far end of the spherical distribution. So z, of course, is given by 1 plus z is 1 over a at the time t minus delta t, right? Because we're looking a little bit earlier. And a of t minus delta t is, of course, 1 over a of z star or t star minus this quantity delta a that we just computed. So let's write that. Delta a is this quantity. I can factor out an a of t star times 1 minus h of t star times delta t. That's just plugging into this expression what I know delta a to be. And now h of t star I can figure out, but before that, this is clearly begging to be expanded using the Newton approximation. If delta t is much smaller than h, I can approximate this as 1 over a of t star times 1 plus h of t star delta t. And now I rewrite that. 1 over a of t star is just 1 plus z star. And then I have h of t star divided by a of t star. And now I'm going to plug in my value for delta t. Delta t is d0 divided by c, and the 1 plus z star I'll replace by a of t star. And now I clean that up, and I see that 1 plus z is 1 plus z star. Of course, that's reasonable. And then the next approximation is just d0 over c times h of t star. So cleaning all that up, I have that, canceling the 1's now, z star is z minus this amount. So this is my estimation for delta z. I have that delta z is h of z star times d0 over c. And we now have a reliable expectation. Remember, we know d0. Measure the correlation, say, using the Lyman alpha forest, between what does observing a cloud at one redshift predict about observing clouds at other redshifts. You should expect a peak near a particular redshift related to this distance d0 by that. And so this gives you lots more information. And if you find the correlation, you have measured the Hubble constant at any particular z. Again, measuring the Hubble constant tantamount to knowing the function a of t. Since this is all occurring in the dust-dominated universe for the majority of the time, this gives us a very sensitive measurement of omega dust, the rate at which the dust-dominated universe is expanding, and we'll use this to narrow down our understanding of the cosmological parameters. Cool.